Hello and welcome to Civil Engineering Mathematics A, Program 3. My name is Eric Tune. I'm a lecturer in mathematics at Central TAFE. In Program 2 we looked at geometry. We made a start with geometry. We talked about concepts such as lines, and we then continued with some simple examples on parallel lines. Today we continue with geometry, but we will concentrate on triangles and quadrilaterals. Now generally there are a lot of definitions and a lot of concepts covered in this program. It's not very difficult, but a lot of terms that you must know. An engineer deals with geometric concepts on a daily basis. Well, let's have a look what is covered then exactly in Program 3. And here we go, overview Program 3. We look at polygons first. Then we have a look at different types of classifying triangles, points of concurrency. I'll tell you about that more when we get to it. Congruent triangles, similar triangles, they are quite important, probably more important than congruent triangles. And we finish off with the classification of quadrilaterals, and we'll do some examples on quadrilaterals, calculate perhaps an area of a parallelogram. Well, without further ado, let's get started. Let's first of all look at the definition of a polygon. Now, it's a simple closed curve that's made up of line segments. It has to be straight line segments, but there are different types. There is a convex one, and in a convex one every angle is less than 180 degrees. For instance, a hexagon. Now that particular shape occurs a lot in nature. Think of beehives, for instance. And polygon can also be concave, and in that case you get an angle that might be bigger than 180, like in a kite. A kite is a typical concave polygon. Now there are various types of polygons, and some of them have been given quite complex names. Of course we know some very easy ones like the triangle. So let me now go through a list of these names. First of all, we look at the triangle, that's got 3 sides. We look at a quadrilateral, 4 sides. A pentagon, think about that building in Washington, that's exactly in the shape of a 5-sided polygon. We look at hexagon, talked about that earlier. Octagon, it's got 8 sides. And then a decagon has 10 sides. Now it is possible to work out the angle sum of each of these polygons, but before you do that you have to know how to get the angle sum of a triangle. It's actually quite easy. If we have a look at this problem, why is the sum of the interior angles of a triangle 180 degrees, then you should draw a line parallel to one of the sides. I've done that here in the diagram. We've got AB, a side of the triangle ABC. I draw this line parallel to AB. And what happens then is that that green angle there, let's call it the green angle, is repeated over there because those two are in corresponding position. That yellow angle there, that is repeated over there because that is in what's called alternate position. In fact, I've written that down here for you. And clearly the black one plus the yellow one plus the green one, if you add those up, will add to 180 degrees. The angle sum in a triangle is 180. Now knowing that, you can actually work out the angle sum of other polygons, like for instance a quadrilateral, because a quadrilateral you can basically split up into 2 triangles. So that should be 2 times 180, 360. Here we go. I've got here a list, the name first of all, we know 180. We know a quadrilateral then must be 360 because it's got 2 triangles in it. I've also listed here the angle if the polygon is regular. See, you just then divide by 3 in that case. You divide there by 4. And regular quadrilateral, by the way, is called a square. Pentagon, 108. And an hexagon, the total is 720. Each angle is 120. And here we get the mathematics into it. Here we've got a formula for n-gon, a general polygon. And we always get 2 less than the number of sides multiplied by 180 to get the total sum of interior angles. Now that enables us to do certain problems. For instance, I've got the problem coming up about the duodecagon, fancy name that is. Let's have a look at a duodecagon is a regular 12-sided figure. What is the interior angle equal to? Well, we know that the total sum, or I shouldn't say total sum, it's just the sum, isn't it? 10, 12 minus 2 is 10, lots of 180. It's always 2 less, so that becomes 1800. And if we then divide 1800 by 12, because a duodecagon has 12 sides, you end up with 150 degrees. 150 degrees is already quite close to 180. You can see that the more sides you're going to have in the polygon, the interior angle increases, you know, from a triangle when it is 60 degrees to a square when it is 90 degrees. Now we've got an angle there of 150 degrees. So that process, if you make a polygon with more and more sides, the angle becomes bigger and bigger. Now let's have a small break and then we come back with the classification of triangles. There are various ways of classifying triangles. One way is by means of an angle, you know, looking at the angles, and the other way is by looking at the side of a triangle. Let's first of all have a look at classification by angle. And you can have here an acute triangle if all the angles are less than 90 degrees. A right angle has one angle equal to 90 degrees, and we always use that symbol there. And an obtuse triangle is one where one angle is greater than 90 degrees. That would be this angle over there. So that's classification by angle. Go on to classification by side. We can have an equilateral triangle. Fancy words these are, I know, they're difficult to remember, but that's the way they are. An equilateral triangle's got 3 sides the same. As a result, the 3 angles there are the same too. An isosceles triangle, and have a look at the spelling. It's got 2 sides the same, meaning that those 2 base angles are going to be the same. And then we've got finally a scalene triangle where all sides are unequal and all angles are unequal as a result. You can actually do some exercises with that, knowing some of these properties of triangles, and I've got a couple here. The first problem I've got is where we've got a equilateral triangle here, we've got a right angle there, and we want to find the value of x. Now that is generally called a pronumeral. The value is actually known. You shouldn't really call it a variable. The value is known. It is designated x as such. Well, how do we do that? Here's the diagram redrawn. If all these angles are, all these sides are the same, then all the angles are the same. So each of them is 60 degrees. That one is 90 degrees. Together 150 degrees. Take it away from 180, and you end up with 30. You don't have to put the little degree sign there because that's already there for the x. See? Let's now look at number 2. A little bit more difficult. We go here with a triangle where we know 2 angles, one 45, the other one 25. We've got these sides the same. The first thing we would do is to calculate that angle there, the remaining angle there of that triangle which has 25 and 45 degrees. If you add those, subtract it from 180, you get 110 degrees. Now as soon as that angle is 110 degrees, then you know that that angle there to the left is 70 degrees, because together it must be 180. Because it's isosceles, the angle there in the top will be 70 degrees as well. See, I've indicated that here. Once you know 70 and 70, then the total must be 180, and we can actually get x, and it becomes 180 minus 2 lots of 70 is equal to 40 degrees. Associated with every triangle there are some important points. There's one especially important in engineering application, that's called the center of gravity. Now those points are actually called points of concurrency. So the definition of a point of concurrency is when 3 or more lines pass through the one point. And like I said, there are 4 points of concurrency associated with a triangle. The first one, let's have a look, the in-center. Now that's the point where so-called angle bisectors intersect. What is an angle bisector? Well, we've got an angle here, we bisect that angle, draw that particular line. And we do that for each of the angles, and we get this yellow point. and you'll find that that is the in-center, and in fact a circle can be drawn and will touch each of those three sides. The second point of concurrency is the circumcenter. That is sometimes outside the triangle, like in this particular case. It's where the perpendicular bisectors intersect. Perpendicular bisectors are those lines that are perpendicular to a side and bisect the side. See, that yellow point there is the perpendicular bisector. A third one, well, I said here, the circle can be circumscribed. That means you can actually draw a circle around all these points. The orthocenter is the point where the altitudes intersect. Altitudes are simply the heights of each of the points. There you go. You go from a vertex to the side opposite at a right angle. That's called the orthocenter. And finally, probably the most important one, it's the centroid. Now that is the point where the so-called medians intersect. Now what's a median? A median is a line that goes from one point there to the middle of the side opposite. Once you draw three of those, you get that point called the centroid, or sometimes called the center of gravity. The center of gravity is a very important concept in engineering. Say you design a car, you want to know where the center of gravity is. There are some very interesting mathematical properties of centroids. For instance, the centroid cuts the median in the ratio 2:1. But then you study advanced geometry and you learn about those things. Okay, we will have a short break and then we come back with looking at typical problems to do with concurrency and similarity. In this section of the program we look at congruent triangles and similar triangles. Now congruent triangles are triangles that are exactly the same shape and size. Work with congruent triangles involves constructions and proofs. They're not so important in engineering applications. Similar triangles are far more important. Still, we have to know what congruent triangles are. So here's the definition. Two triangles are congruent if they have the same shape and size. In that case, each angle in one triangle has an exact equal angle in the other, and each side has an equal side in the other. Let's have a look in this diagram. You clearly see that there are two yellow angles there. There is that side there, that purple side over there, and everything corresponds exactly. Now it's very important that when you deal with congruent triangles that you get the order correct in which you name the triangles. And I've got that written out here. If you have this triangle ABC, for instance, and there's this other one that's congruent to it, X, Y, Z, then you can't just name them willy-nilly and say ABC is congruent to X, Y, Z. Now you have to make sure that they match up. So you mention A first, then you should also mention the one that corresponds to A in the second one, and that is angle Z there. And B corresponds to Y, as you can see, and C corresponds to X. It's very important. Now what do you do with congruent triangles? Well, let's first of all have a look at some conditions for congruency. There are in fact four. The first condition is side, side, side. That's generally referred to as SSS. And in that case, if there are three sides that are congruent to three sides in a second triangle, you can say that the triangles are congruent. The other condition is side, angle, side, and the angle is then in between the two sides. In that particular case, that green angle there is in between these two sides. So if you have a situation where this is known, that is known, that is known, that is known, and the two angles are the same, you can say the triangles are congruent. Third condition, angle, side, angle, or referred to as ASA. And there, the side is between the two given angles. See, this green angle corresponds there. The side is between the two given angles. And then the fourth one, and that is used most of the time, that is the right angle hypotenuse side, RHS. And if you know the hypotenuse of one triangle and the hypotenuse of the second one, and they're equal. You know there's a right angle there and a right angle there. You know those two sides correspond, and those two triangles are congruent. Congruent triangles are used a lot in proofs, in geometric proofs. Now it's not really part of this course so much, but I still want to show you one proof involving congruency. It's such an important concept. So here we go. Let's have a look now. We've got a triangle here, and we have to show that in this isosceles triangle, the bisector of angle C, that's the bisector of angle C, is actually perpendicular to AB and actually cuts AB in half. Now, to do that using congruent triangles, you show that the triangle ADC is congruent to BDC, and I've used the correct matching up. It's the SAS condition. If that is the case, then those sides there, AD and BD, must be the same, because they're exactly the same, those two triangles, and also these angles at the bottom, ADC and BDC, must be the same. Now, because they become a 180-degree line, if they are the same, each of them must be 90 degrees. So I've actually shown, using congruency, that AD is DB, so it bisects the base, but I've also shown that these two angles are 90 degrees. Hence, CD is the perpendicular bisector of AB. Quite a difficult concept, but we don't really use it that much in engineering. What we use are similar triangles. Now, similar triangles have the same shape. They don't necessarily have the same size, but they have the same shape. Official definition coming up. We have two triangles are similar if they have the same shape. So here I've got two similar triangles. You see they're not the same in size, but they're certainly the same in shape. These angles match up, and what happens with a similar triangle is that the sides will be in proportion. They will be in proportion. That's a very important concept. There are, again, notation conventions, and of course you do exactly the same as you would do for congruent triangles. You match them up exactly. In this particular, A corresponds to Z, and B corresponds to Y, and C corresponds to X, and that's why I should write it down like this. Triangle ABC, and that's the sign for similarity, is congruent to triangle ZYX. So A should correspond to Z, and I've got that correct there, C. There are, as with congruency, conditions for similarity. In fact, there are three, and I'll go quickly through those before we get into some problems. The first condition is AA. If two angles are similar to, are the same as two angles in another triangle, then the triangles are similar. Example here, we've got two triangles, 34 and 113 degrees, 34 and 113. Of course, those must be the same too, because each has to add up to 180. The next condition is included angles equal and two pairs of corresponding sides in proportion. A bit more difficult, but I've got it again, an example here. That angle is the same, and these sides are in proportion. In fact, there's an enlargement happening of a factor of 2. That 6 becomes 12, the 3 becomes 6, and so everything is doubled. In fact, the enlargement factor is 2. And the third condition, 3 pairs of corresponding sides in proportion. So again, an example. See, in this case, 4 has become 6, 8 has become 12, and 6 has become 9. That is an enlargement factor of 1.5. Well, that was a lot of theory. Let's have a bit of a breather, and then we come back with some practical examples of similar triangles. Well, let's get started with some typical similar triangle problems. Problem 1, an easy one. We've got the triangle here. We want to find that side N. Now, the big one is similar to the small one over there. And if I write down the correct ratio, then I can say that N divided by 4, because those are in proportion, must be equal to 5 divided by 3 plus 5, which is 8. And if you do that, you get n equals 2.5. It's an enlargement factor again, isn't it, of 2, 4 to 8. So that must be also 2.5. 2 times 2.5 is 5. Bit more difficult problem coming up. Here the triangles don't look similar, but I'm talking here about x, d, z and y, x, z, the big one. Now, why are they similar? Because those ratios are the same. The sides are in the same ratio. 2 is to 3, 2 is to 3, 2 is to 3. Takes a bit of checking, but that is the way it happens with similar triangles sometimes. Hence, they are similar because the sides are in proportion. Let's have a look at a practical problem now, because it's all very well having this. It's a little bit more theory. A practical problem would be, say, finding the height of a building, for instance, or in this case, the height of a boy we want to find. We know that a boy is standing 20 meters from a building, and it's casting a shadow of 2 meters. He is 160 centimeters tall. How tall is the building? So we actually have to find the building height. So in diagram form, that is the shadow of the boy, 2 meters. He is 1.6 meters tall, 160 centimeters. He's standing 20 meters away, and that is the height of the building, that x. In proportions, we get x divided by 1.6 equals 2 plus 20, which is 22, divided by 2. And if you then multiply that out, you'll get 17.6. We spent all our time so far on triangles, but of course we also have to discuss quadrilaterals. There are different types of quadrilaterals, and I've got them classified on the screen. Let's have a look. We've got, first of all, a trapezium. That's got two sides parallel. So if the two sides parallel, it's a trapezium. A parallelogram, on the other hand, has two pairs of sides parallel. See, that one is parallel to that, and the sides there are parallel. One property would be that the diagonals bisect each other in a parallelogram. You can prove that using congruent triangles. The third type is a rectangle. We can call a rectangle an equiangular parallelogram. It's got the same angles. There you got it, all 90 degrees. And the diagonals again bisect each other. Now, a rhombus, special form of parallelogram, it's an equilateral parallelogram. It's got the same sides, not the same angles, the same sides. See, there we've got a rhombus. Finally, we get to a square, which can be described as an equilateral rectangle. There we've got it. Or an equiangular or equilateral rhombus. Another definition would be an equilateral, an equiangular parallelogram. Yeah, fancy terms, I know, but they are used, those terms. Now, how are the square, the rectangle, the parallelogram, etc. related? A lot of mistakes are made with that. I've actually got quite a nice diagram here, and I'm pretty proud of the way that is constructed. We've got a quadrilateral, any four-sided polygon. That can become a trapezium if you make two sides parallel. It can become a parallelogram if you make two pairs of sides parallel. And now you have to split them up. You split them up into a rectangle and into a rhombus. So a rhombus is not a rectangle. Yeah, they're completely different things. They're both parallelograms, but they're not, one is not the other. Once you then make special conditions again, you get back to what's called a square. So there you've got the diagram, the classification of quadrilaterals. There's only time in this program to do one quadrilateral problem. You should try some from your book. Here we've got a typical problem. Find the perimeter and area of this parallelogram. Well, the perimeter is easily found because that's just 60 plus 45, two lots of that. And that becomes 2 times 105, 210. For the area, we use a little trick. We can transfer this part to that part over there, as I've done in the diagram. And then you create a rectangle, which is 30 meters by 60 meters. And of course, the area of that is 1800 square meters. Now, you should practice some problems from chapter 5 in your book. Well, this is the end of program 3. Thank you for joining me. I'm looking forward to your company in the next program.